Good morning, everyone. Thanks for waking up early, and it's my pleasure to introduce the speakers for the first session on quantum. So our first speaker is Mingnan Zhao, and he will talk about quantum pseudorandom scramblers. And yeah, the floor is yours.
Thanks for the introduction. Today I'll talk about quantum pseudorandom scrambler. And this is joint work with Chu Han, Minlong, Fang, and Peng Hui. So we know in computer science, randomness is a useful resources for computing, but sometimes it is very costly to generate true randomness. So pseudorandomness becomes an important topic in computer science. It refers to objects that look truly random to adversaries who don't have unlimited power. So typically, the true randomness is a uniform distribution on a very large set S, and the pseudorandomness involves some distribution over a smaller set T, which allows for efficient sampling. And for the adversary, we often model them as polynomial time randomized algorithms or quantum algorithms. And if the adversary with bounded power cannot distinguish those two objects, we then say they're computationally indistinguishable. And if the adversary with unbounded power cannot distinguish those two objects, we then say they're statistically indistinguishable. In quantum cryptography, Giulio and Song proposed two interesting pseudorandom primitives. The first one is PRSG, which stands for pseudorandom state generator. It is an efficient quantum algorithm G that takes a key K as input and output an n-qubit quantum state phi K. When random sample a key, the quantum state phi K is computationally indistinguishable from a hard random state psi, even if we gave the adversary polynomial copies of the state. We call the state phi K the pseudorandom state, or PRS. So PRSG exists assuming the existence of quantum secure pseudorandom functions. The construction is to apply Hadamard gate on all zero state and then query the pseudorandom function on the face. And you can use either binary phase or complex phase. PRSG are very useful to develop novel primitives, including quantum money scheme and quantum bit commitment scheme. And also PRSG attracts the attentions from the researchers in the field of quantum gravity theory as they model the black hole as a pseudorandom state. Another primitive is the pseudorandom unitary operators, or PRU. PRU is a set of unitaries UK indexed by a key K. And every UK can be implemented via a very efficient algorithm G if we gave the key K as input. So when randomly sample a key, the unitary UK is computationally indistinguishable from a hard random unitary U if we gave the adversary the oracle access to the unitary we sampled. PRU is a very interesting primitive. It is a quantum analog of PRFs in classical cryptography. So it is believed that PRU may hold significant potential for various applications in quantum cryptography. And moreover, it is shown that PRUs exist even if one-way function doesn't exist. So this suggests a weaker assumption for quantum cryptography. However, how to construct the PRU remains an open problem until very recently. And PRU is a very strong primitive compared to PRSG. A simple argument shows that if we take an arbitrary pure state phi and we apply the PRU UK on phi, then the resulting state UK phi is computationally indistinguishable from a hard random state. In other words, PRU maps an arbitrary pure state to PRS. However, in PRSG, the algorithm G may need a fixed initial state and may fail if we change the initial state. For example, in the construction we mentioned before, the initial state is all zero state. So, and it is also unclear how to construct an efficient quantum circuit to map an arbitrary pure state to PRS, which is a modest property of PRU. So considering there seems to be a huge gap between PRU and PRSG, so people will ask a question that, can we build something between PRU and PRSG to bridge the gap? And our answer is that we propose a new primitive, which is called pseudo-random state scrambler, as it scrambles any arbitrary pure state to a PRS. One thing I would like to mention here is that very recently, Ma and Huang proved that PRU exists assuming the existence of quantum secure Orient functions by developing a very useful compressed purification technique for analyzing quantum pseudorandom unitaries. And our construction and analyzing is quite different from their construction and analyzing. And also our construction has additional randomizing property, which is of independent interest. Okay, so in this work, we first gave the definition of our new primitive, which is pseudorandom state scrambler, or PRSS. And we gave a construction of PRSS from quantum secure pseudorandom permutations and pseudorandom functions. So the construction is basically to simulate a new random walk we propose, and we call it the parallel Kex walk. And this random walk can converge to the Haar measure on unit sphere in polynomial time, which is an exponential speedup compared to the original one. And then we find an interesting property we call the dispersion property of our scrambler. It says that the output state of our scrambler forms an epsilon net on the sphere. And we also gave some applications of our PRSS. So the definition for PRSS is that let H be a Hilbert space with dimension 2 to the n, and lambda be the security parameter. We see a family of unitary operators Rk indexed by key k is a PRSS if the following three conditions holds. The first one is the key length is bounded by a polynomial, so we can efficiently sample the key. And for every Rk, there is an efficient implementation of the unitary. And the third condition says that for any pure state phi, if we randomly sample a key k and we apply Rk on phi, then Rk phi is computationally indistinguishable from a Haar random state psi, even if we give the adversary polynomial copies. So if Rk is a PRSS, then we know for any pure state phi, Rk phi is a pseudorandom state. And also if Rk is a PRU, then it is also a PRSS. Then by strengthening the pseudorandom condition in PRSS, we obtain the definition for random state scrambler. In random state scrambler, we require that the output state of our scrambler is statistically indistinguishable from a Haar random state, which means the trace distance between two states are negligible. So to construct an PRSS, we first construct an RSS with random permutation and random function. We show for any pure state phi, Rk phi is statistically indistinguishable from a Haar random state. And then we replace the random permutation and random function in Rk with pseudo-random permutation and pseudo-random function. Then we obtain Rk prime. By the security of pseudo-random permutation and pseudo-random function, we know Rk phi and Rk prime phi are computationally indistinguishable. Then by the triangle inequality, we know Rk prime phi are computationally indistinguishable from a Haar random state. So this establishes that Rk prime is an RSS. So from now on, we mainly focus on how to construct an RSS and show its output state is statistically close to a Haar random state. Our approach is that we will first give a definition of a novel random walk, and the random walk will produce a state in polynomial steps, and the state is statistically indistinguishable from a Haar random state. And then we gave an efficient construction using a quantum circuit to simulate one single step of the parallel Kex walk. So we mainly explain how to construct an RSS in the real Hilbert space, and for the complex space, it is easy to extend to the complex space using the same idea. So let's first look at a random walk, which is scrambling a quantum state. So we will propose a parallel version of this Kex walk. So the original Kex walk on the unit sphere first selects two random coordinates ij and random angle theta, and it rotates xi, xj by the random theta. So yeah, this random walk is originally from a model for Boltzmann gas, and it is extensively studied in mathematical physics. It is proved that this random walk converges to the Haar measure in the unit sphere in n times 2 to the n steps. And there is another variant of a Keck walk on the special unitary group. So the new random walk we propose is a parallel version of the Kex walk we call the parallel Kex walk. So in this random walk, we will first select a random perfect matching of all coordinates denoted by p. So there are 2 to the n minus 1 pairs in p. And for each pair, in P, we will sample an independent angle theta k, and we rotate the pair to the corresponding angle theta k. So intuitively, one single step of the parallel Kex walk can be viewed as 2 to the n steps of the original Kex walk. So we expect this random walk has an exponential speedup and converges in polynomial steps. However, the pairs being rotated in this parallel Kex walk are distinct, thus not independent. So the original result in Kex walk cannot directly apply here. So unfortunately, we can prove the following theorem. So let phi t be the parallel be the output state of t steps of parallel Kex walk. Then for t is large enough, then the output state phi t is statistically close to a hard random state. And this a single step of parallel Kex walk can be implemented via a quantum circuit denoted by k sigma f. Here sigma is a random permutation and f is a random function. Roughly speaking, the sigma is used to partition the basis into 2 to the n-1 pairs, and the random function is used to sample an independent angle for every pair. Then repeat the circuit for t steps. We have circuit C, which represents the t steps of the parallel Kex walk. Then we know the output state of C is statistically close to a hard random state, which means C is an RSS. Then by replacing the random permutation random function, we obtain a construction for PRSS. So till now, we have given the definition, and we have shown how to construct RSS and PRSS. Surprisingly, by deeply exploring the parallel Kex walk, we find an interesting property of our scrambler we call a dispersion property. So start from an arbitrary pure state on the sphere, and we apply parallel Kex walk for about n steps. Then the output state of the random walk will be supported on the whole unit sphere. And the definition, the distribution on the sphere is close to hard measure in total variation distance. And as for our RSS, it can be viewed as a discrete version of parallel Kex walk. And the output state of our scrambler is spread over all the unit sphere, and they form an epsilon net of the state space. And the distribution on this epsilon net is close to hard measure in Western distance. And this property is not a necessary property by the definition of RSS or even for PRU. And this property is not possessed by a regular pseudo-random state, for example, the random phase state. So you can see the random phase state, the amplitude for every basis are equal, so they are highly constructed and concentrate on the unit sphere, highly concentrated on the unit sphere. They're only close to hard measure in average. So we think our scrambler is much powerful than PRSG, and it has a very interesting, strong dispersing property. So, okay, let's make some final remarks and give some open questions. So in this work, we propose a new primitive called PRSS, and it is able to scramble an arbitrary pure state to a PRS. So one question might be, is our scrambler or is our construction a PRU? And our answer is yes. We can prove that our construction is a PRU using the powerful compressed purification technique developed by Huang and Ma. And the second question is that, is there any applications of our PRSS, for example, some application that makes use of the dispersion property we have introduced before? And the third question is that, can we simplify our construction, for example, to make it more local or to make it to meet the requirement of the near-term quantum devices? Yeah, thank you. That's all I want to share today.